I'm Adriana Brown.
I'm Sanchez Wathia.
I'm Neha Deshpande.
I'm Reese Gow. I'm Jacob Allen.
I'm Stu Duso.
I'm Timothy J. Avini. Welcome to CS 1332 Recitation on a snow day.
And now for some preliminary announcements. Don't forget that your Homework 3 Stacks and Cues has been released. If this is news to you, you should stop watching this video and get to that right now because that is due tomorrow. Yes, tomorrow, January 30th at 11:55 p.m. That's January 30th at 11:55 p.m. Get to that right now if you haven't done so already. Speaking of your homework, tomorrow your Homework 4 Binary Search Trees will release. That'll be a 2-week homework to give you time to focus on the exam due 11:55 p.m. on February 13th. Speaking of things that release tomorrow night we will release the practice exam for Exam 1. Next recitation, we will spend some time going over the answers to that exam so you can get an idea of where you are before you actually take the exam. Speaking of your Exam 1 is next week. Make sure you go to the section you are registered for in Oscar, unless you've been told otherwise by Dr. HB. Make sure you bring your buzz card with you to the exam. We will be scanning them to verify your identity. Also, stay tuned for some time in this video when we release the magic link to the recitation worksheet.
Thank you, Jacob. That was ribbon. Today, we're going to talk a little bit about trees. Not that kind of tree, but the computer science kind of tree. In computer science, a tree is an abstract data type that has nodes and children, where each child is just another node. These nodes can store data, and in any arbitrary tree, a node can have an arbitrary number of children. Now, in a binary tree in particular, each node has a maximum of 2 children. So this isn't a binary tree, because the C node has 3 children, D, E, and F. We take off some of those extra nodes, right? This is a binary tree because the node B has no children, the node A has 2 children, B and C, the node C has 2 children, D and E, and any node that had 1 child would also be valid in a binary tree. In a binary tree, each node has a couple of properties that are particularly useful to look at when we're building algorithms or just analyzing the structure of the tree. In this tree, each node has a depth. The depth of the node is just the number of edges from the root to that node. So the depth of the root is 0 because it is the root. There are no edges to get there. The depth of B is 1 because it takes 1 edge to get there. The depth of C is 1. The depth of F is 2. The depth of D is 2, the depth of G is 2, and the depth of E is 3, because it takes 3 edges to get to E from the root. Each node also has a height. Now, the height is just the number of edges it takes to get to the deepest child of that node. So naturally, leaf nodes have a height of 0, because we're already at the deepest child. We would consider a null node to have a height of -1, for reasons you'll see they kind of work out mathematically. The node D has a height of 1 because it takes 1 edge to get to that deepest node E. The node C has a height of 2 because the deepest node in the subtree is E, and there are 2 edges to get to E. The node B has a height of 1. There's the 1 edge to get to F. And the node A has a height of 1, 2, 3. It takes 3 edges to get to E from A, and E is the deepest node in A's subtree. Now, to determine the height of a node, mathematically or in your code, you'll just take the maximum value of the left child or the right child's height and then add 1. This is because the height of the left or the right child is going to be based on the deepest node in that subtree. So if we take the bigger of the 2, we'll find a height based on the deepest node in the whole thing, and then we just add 1 for the edge that it took to get to the left or the right. This isn't the last time you'll see how recursive the nature of these trees can get. We do these operations on subtrees. That is, a node that's the root of kind of its own smaller tree inside the larger tree. And then we can find out the answer to the big question, what's the height of the entire tree, by finding the answer to smaller questions. What's the height of this node? And what's the height of that node? And then we can combine these answers to get an answer to the bigger problem.
So now we're going to talk about the shape property in binary search trees. So the first thing we're going to talk about is full trees. So in a full tree, every node has either 2 children or 0 children, which are the leaves. Next, we're going to talk about complete trees. So in a complete tree, all the levels in the tree are filled, except for the last level where it's filled from left to right. Next, we're going to talk about degenerate trees. So in a degenerate tree, all the nodes have 1 child, as opposed to a BST where they can have 2. So this generally functions as a linked list. So some use cases of trees involves they have trees in compilers, storing files on disks, and coding, and we'll talk more about trees in future lectures in 1332.
Now we're going to talk about binary search trees. What makes binary search trees the best kinds of binary trees is that they have this new added order property. The data to the left of a node is going to be lesser than the data of the current node, and the nodes to the right of the parent node are going to contain data that are larger. This also means that all the data in the nodes have to be comparable. This just means that we are going to use the compare to method to compare data. We're gonna be back after a quick break. Now we're going to do a searching example with a BST. When we're looking for data in a BST, what we do is compare the data that we're trying to find with the data in the current node. If the data that we're trying to find is less than the data in the current node, we're going to want to recurse to the left. If it's greater, we recurse to the right. And if it is equal to the data in the current node, that means we found it. But if we reach a null spot, that means we've searched the entire BST for the data and we haven't found it. So we return null. Let's do a quick example. Let's try to find Waldo in this BST. What we're going to do is compare Waldo to the data in the current node, which at this point is a root. In this node, we have mom, and m is less than w, so we're going to want to recurse right because Waldo is going to be greater than mom. We're going to recurse right and check the next node. Tim is still less than Waldo, so we want to go right until we find Waldo.
So now we're going to talk about adding to a BST, and when we add to a BST, we perform the same algorithm on the tree as when we were searching. So in this example, let's say we're going to try to add a 60 node. And there are actually 2 different ways we can add to a BST. One of them being pointer reinforcement, which if you stay tuned, we'll teach you about. But the way you might think to do it is to perform the look-ahead method. And what that means is we'll compare 60 to 50, and when we see that 60 is bigger than 50, we'll have to check 50's right child. And if 50's right child is null, we'll place the node there. But if it's not, then we have to traverse that node. And having this check kind of increases clutter of code, and it's just overall a bit messy to deal with. So that's why later we'll teach you a cleaner method to do called pointer reinforcement. But for now, we'll work through this using the look ahead. So again, when we're adding 60, we'll start at the root, and we'll compare 60 to 50. We see that 60 is greater than 50, so we'll check 50's right child. We see that it is not null, it is 100, so we'll traverse to this node. And now when we're at this node, again, we'll compare 60 with 100, and we see that 60 is less than 100, so that means we'll have to check 100's, we'll have to look ahead to 100's left child. And we see that 100's left child is not null, which means we can traverse to this node. And now that we're at this node, we compare 60 with 75. We see that 60 is less than 75, which means we need to look ahead to 75's left child. We see that 75's left child is a null, which means because we've hit a null, we'll place the node there. So we create a new node with the value 60. And it might seem, you might be thinking that when we compare data, we'll either be using less than, equal to, or greater than. But because we might be comparing Java objects, we can't use these compare Java objects. We need to use the compare to method. If we ever try to add data that's already in the tree, say add 100, this is actually more or less left up to the implementer, but in this class, we'll just have you ignore it. Don't remove this node, don't replace it with this node, just ignore it.
So Reese just went over the look-ahead method for adding to a BST, but for add and remove, the TAs recommend another method called pointer reinforcement.
Yay!
Right? So anyway, the look-ahead method for adding to a BST involved looking at the current node, comparing the data, and then checking the children to make sure they weren't null, so we could either traverse or add. And so all of that code together just gets really cluttered because you have a bunch of conditional blocks, and it's just, you can't really check for every edge case, especially when it comes to remove, or it just gets really messy. So pointer reinforcement actually is a cleaner way to do add and remove that is, it handles a lot of edge cases just the way it is. And so I'm going to put some pseudocode up for add first because I think it'll make a lot more sense if you can see what's actually happening. And then we'll go through the example again. So I'm going to do the pseudocode and you can just cut to when I did it. Okay. So, I should actually put that there. So I'll talk about it actually. So we'll see. And then you had your recursive helper. And I'm changing it, don't worry. I'm gonna be like, what? So, when you actually did the look-ahead method, if you were to write it out, it would look something like this. You'd have a wrapper function that would be void, and it would call a recursive helper function with the root passed in as the first current node, just like you did in the linked list example before. And then your recursive helper would have, again, a void return type, but it would have data and current as its variables, and then you would actually handle the case. However, for pointer reinforcement, we're going to change the helper method a little bit. It's no longer going to be void. It's actually going to have a return type. It's going to have a node that it returns. And in the actual wrapper function, when you call it, you're not just going to call the helper method like this. You're actually going to reinforce your tree by setting the root equal to the recursive call. And this will make a lot more sense as I keep going. Okay, so the reason we do this is because in pointer reinforcement, what happens is when you call this method, you're setting the root pointer equal to the tree. So what's going to happen is when you call this root pointer is no longer going to point at the tree, it's just going to be left hanging. And so now what's going to happen is your recursive method is going to be called, and in the actual recursive method, your terminating case will just be if you reach a null. And again, I'm going to go through the diagramming example again with the pseudocode. So your base case would be that your current node is equal to null. And if that happens, you just return a new node with your inputted data. So you would return new node with the data. Okay? And so now, this looks a little weird, but when you actually start traversing, you're going to sort of do as Reese mentioned, you look at the data and compare, but now you don't actually have to check the children of the current node. So what's going to happen is, if this is your current in the first recursive call, you're going to check, okay, so current is not null, right? And so you're going to check the data. So you're going to say if data is greater than the current's data, what you're going to do is you're going to just set the currents right child, or yeah, I'll call the set right method actually. So current dot set right, and then you would put your recursive call in this method. And so I would put add helper data, and then I would put current dot right. So when you do that, for this example, since we're adding 60, what would happen is, like we left the root hanging here, the current node, its right pointer would be left hanging, because we haven't actually returned anything to the set right yet. Instead, it's going to call the add helper recursively. And so now, in this next recursive call, 100, the right child of 50, is going to be the current. Same thing, it's going to go through, it's going to see current is not null, and it's going to go and check, okay, well in this case, we'd see that the data is actually less than the current's data. And so we'd do something similar to what we did here, except that we'd set left. So set left, and we'd call the add helper on the left child of cur. And so now what's going to happen is we're going to leave this pointer hanging because it hasn't been set yet. And so now there's going to be another recursive call for 75. Same thing, it's going to get to this case. It's again less, so we're going to have this pointer hanging. And then now we're finally going to get to recursive call where this null here will be current. And when this happens, we're going to return a new node with the inputted data. And so what happens is that we're creating the new node here, and we're returning it, and it'll go back in the recursive tray or stack, and it'll go back to this set left for when 75 is current, and it's going to set its left pointer to what we just returned. It's no longer hanging. And so now it's going to go back up the recursive stack, and it's going to go back to the 100, because it's going to, oh, I forgot one thing. And so after doing this crucial step, you have to return cur. And here too, after you set its pointer. Otherwise, nothing would be returned, right? So here, you're going to return cur, and it's going to be set as 100's left child. And then this was cur for its own recursive call, and it's going to be set as 50's right child. And then now, we are going to get back to original method call, and it's going to set 50 as the root. And this is very important because there are a bunch of cases where in remove, when Adriana goes over remove, you're going to see that if you actually do something like remove the root and your entire tree changes, but you never remember to reinforce the root, you're going to lose reference to your whole tree. And doing this is just, it may seem redundant, but it's how pointer reinforcement works. So one more time, if we do pointer reinforcement and look at the pseudocode, we're going to see that what happens is the root is going to be left hanging, and then you're going to traverse, and then you're going to have a recursive call until you reach your base case of where you reach a null, and then you keep returning those nodes back until it all just works out.
So now we're going to talk about removing. The general algorithm for removing is kind of the same as what we've seen before in searching and adding. Essentially, we go through the same steps of searching through our tree, comparing if it's greater than or less than, and traversing down the tree like that. But when we get to actually the data we want to remove, there are a couple different cases we have to consider. The first case is if the node that contains the data that we want to remove has 0 children. If this is the case, it's pretty much our easiest case that we have to deal with, because all we have to do is set the parent's pointer to that child to null, which effectively cuts it out of the tree. So let's add that back in there for our next example. The second case is if the has 1 child. So let's say we wanted to remove 75, who has a single child, which is 90. In this case, all we're going to do is redirect the pointer from the parent of the node we want to remove to whatever that single child is. So let's say if we do want to remove 75, what we do is we essentially take this pointer and we point it at the 90. And this would work if it had a single left child or a single right child. Because if you remember the properties of BST, anything to the left of this 100 is going to be less than it, so redirecting its pointer is going to maintain that order property. So let's fix that. And the final case that we look at when removing is if the node that has the data we want to remove has 2 children. This is a pretty complex case because we can't just redirect one pointer and fix the problem. Let's say we want to remove the 50 that's at the top. This is when we introduce the concept of predecessor and successor. So if you have just a collection of numbers, let's say we have 1, 2, 3, 4, and 5. If we're looking at 3, the predecessor of 3 in this data set is the one that is less than it, but is the greatest within that set. So in this case, the predecessor is 2. And on the opposite side of that spectrum, the successor is the data value that is still greater than it, but the least of that in the set. So in this case, 4 would be our successor. So we're going to do a similar thing in this tree to, instead of messing with the actual structure, trying to manipulate some of these pointers, we're instead going to actually replace the data that we're looking for with one of these values to kind of maintain that property. So let me show you how that works. If we're looking for the predecessor of any value, so let's say we're at the 50, and we want to find its predecessor, we're essentially going to follow a similar pathway down the tree to find it. This pathway is pretty set just because of the order property that BSTs have. So to find the predecessor, you're going to start by going to the left once, and then as far right as possible before you hit something that has a right of null. So in this case, the 25 is the predecessor of 50 because it is the largest thing in the left subtree. So in that case then, we would actually be removing this node and replacing the data that we have in the root. And so essentially what we do by using the predecessor or successor is that we delegate the actual removal of a node to another area in the tree where it's easier to remove. So as I was saying that we find the predecessor only when it has like no child to the right, this guarantees that we're either removing in the 1-child case or the 0-child case for actually removing the node that contains the predecessor's data. Similarly, if we want to find the successor and use that instead, we go to the right once, and then as far left as possible before we hit a node whose left child is null. So the differences between using predecessor and successor really don't matter. Essentially, it's just an implementation choice. I believe in our homework we were asking you all to use the predecessor, so that is what we're going to go with in our examples moving forward. So here's some pseudocode for removing from a BST using pointer reinforcement. The first method that we have is the public method. This would be the method that users would call and pass in a single piece of data because they don't need to know about the nodes in the tree. So the first thing that we're going to do is we're going to create a dummy node. And this is important because we want to actually be able to return the removed data to the user that was in the tree. But since we're using the recursive return values to actually be changing the tree and returning nodes, we can't really do this. So some people might think that you could just create a parameter that's maybe of the same data type called dummy and then just change that at the end and return it. But unfortunately, you can't do this in Java. So what we're doing instead is we're creating kind of a container that we're going to be passing through all of our recursive calls that's going to point to a constant space in memory that then we'll be able to access after all the recursive calls have executed and we can finally return the data. So this might be a little confusing right now, but as we kind of go through the method and see how we use the dummy node, this is hopefully will start to make a little bit more sense. So the next step that we do after creating this dummy node is we're going to set the root equal to the recursive helper called on the root. So what this is going to do is that technically the root pointer is a pointer that needs to be reinforced as well. And as Sanjana mentioned, it's important to reinforce the root because there could be changes that take place on the root. So after we do this, we're just going to return the dummy node's data because the recursive call is actually going to be taking care of removing the node from the tree. So now let's take a look at the recursive helper method. So this is essentially going to be a private helper method that's going to take in a parameter of a node, which is your current node, the data you want to remove, and the dummy node that we talked about before. So the actual comparisons are going to look pretty similar to when we did add, because the first thing you're going to do is check to see if the node is null. If the node is null, that means the data is not found. The data is not found. And in this case, you can either throw an exception, you can return null, something like that, that'll just alert the user that nothing was able to happen. Then the next case we're going to look at is if the data equals the node's data. So in this case, we're going to go ahead and we're going to set the dummy node's data to the data from the tree. Make sure that you're not setting dummy node's data to the parameter data itself, because in Java, just because equals is true doesn't mean the two objects are exactly the same. And we've discussed this before when talking about object equality versus reference equality. The next step that we have to do is look at the different cases and see which one our removal is going to fall into. In the first case, if there are no children, if both the left pointer and the right pointer of the current node are null, we're going to return null. Because this means what we can do is return null back up to that single pointer that we've just reinforced of the parent. The second case is if there's only one child. So in this case, you can check to see if maybe one pointer is null while the other is not, and vice versa. The last case we're going to look at is if there are two children, which is pretty easy to check for because then both of the children just aren't going to be null. So what we're going to do in this case is we actually have to kind of create another set of steps. So what we're going to do is create another temporary dummy node to go down into our left subtree to try to find and extract the predecessor data. So we're going to delegate this call over to another helper method that we're just going to call the predecessor helper. This is important to have another separate helper to both get the data and remove it, because we don't want to just call remove again after iterating down and trying to find the predecessor, because we just want to avoid having to traverse the tree multiple times. So let's take a look at the predecessor helper method. This is essentially going to look like a mini remove method. We're going to take in a parameter which is current, and we're going to have the temporary dummy node. So in this case, we don't actually have a data parameter because we're not looking for anything specifically. We're not looking for a value, we're looking for a position. So in that case, our base case is going to be if the node's right child is null. If the node's right child is null, that means we found the predecessor. So in this case, we're going to set the temporary node's data equal to the node's data. And then we're going to return node's left. So what this does is returning node's left takes care of the cases if the predecessor node has either 0 children or 1 child. If the predecessor has only 1 child, then it's definitely going to be on the left, because if it's on the right, that means we haven't actually reached our base case. So by returning node's left, we can take care of returning that child in the 1 child remove case, or if it's null, then we take care of that as well. If we haven't reached the predecessor yet, we're going to keep calling this recursive method on the right until we hit there. So essentially our else statement is we're going to set node's right equal to a recursive call to the right using our predecessor helper method. At the end, we're just going to return the node. So this essentially delegates to those cases where we were recurring to the right because we hadn't actually reached the predecessor yet. When we did reach the predecessor, we were returning something different because that was the only node we wanted to change. After this method executes, we come back up to our original private helper method for removes. And now we've reinforced the node's left pointer to that new subtree that has the predecessor's node removed. When we do this, we now set the current node's data to the temporary node's data. And essentially what this does is it replaces the current node's data that we're at with the predecessor's data without having to make any changes to the pointers that the node has or maybe any pointers to that node. And so what we're doing here is we're replacing the data without having to mess with any of the pointers that are pointing at it. You can kind of think of this similar to how we did some of those circularly linked list tricks by being able to manipulate data without having to manipulate some of the pointers that may have been harder to reach. And of course, after this, we're just going to look at those similar traversal methods that we had in add, where essentially if the data that we're looking for is less than the current node's data, we're going to recur to the left. And if the data that we're looking for is greater than the current node's data, then we're going to recur to the right. And at the end of this, we're going to return node. And essentially, as I stated before, when talking about the predecessor helper method, when you return node at the very end, this is a very key line because it's going to reinforce all of the nodes that weren't changed back up the tree. And then you return back up to the public method. And now you've successfully removed some data from your tree.
Alright, so now let's do an example of removing from this VST using the pointer reinforcement technique that I just went over. So, let's say we want to remove 100. We're going to start out by calling our method on the root. So when we're at the 50, what's going to happen is we're going to start by comparing the data that we're looking for, 100, to the data that we currently have, which is 50. We see that it's greater than what we want, so essentially we're going to make the recursive call to the right. So this is going to put this pointer kind of in limbo as we start making changes to the tree. Then when we reach the 100, we compare the data, see that it's equal, and now we have to go through and consider all the different removal cases. We check to see the status of its left and its right children. We see that both of them are valid, so we have a 2-child remove case. Now what we're going to do is we're going to make a call to our predecessor helper method to then find and remove the data of the predecessor. So to do that, we're going to start by calling that method on 1 to the left. And this is going to take care of just going to the left once so that our predecessor method can just kind of go as far right as possible. So when we do that, we put this pointer in limbo as well because we don't know what that's actually going to point to yet until those methods start returning. Then when we get down to the 75, we're going to look at the predecessor method. and we're going to say, all right, is the right child null yet? And it's not. So in this case, we're going to go to this one, put this pointer in limbo as well, and when we reach this 90, we say, all right, is this right pointer null? And it is. So that means 90 is our predecessor. So what we're going to do is we're going to save this data in our dummy node to kind of push back up to where we started the removal, and then we're going to actually return null up here. Another way you can do this is what is written in the pseudocode, is you can just return the left child, because this will essentially take care of both the one child and zero child remove cases if your predecessor has either of those cases. So by returning the left child here, that's null. So this pointer now points to null. And now when we get back up to the 75, we didn't actually change anything here, so we go ahead and return 75 again, which reinforces this pointer here. When we get back up to the 100, we now have that dummy node data that we saved from removing the predecessor. So we can now save the 100 in that other dummy node that we have for returning back to the user at the end. But for now, we're going to replace its data with the predecessor data that we just found. And so when we do this, we're essentially done with that. And then we can return back up here. And since this node wasn't actually changed, all that we did was change the data inside of it, we're still going to go down to that last call where we say return node. And when we return node, this pointer is reinforced. So 50 now points, 50's right child now points to this 90. And then we come back up to the root, nothing else was changed there, so we return the node. And now root is set back to 50, which then reinforces the root as well.
All right, so now we're going to do another example of doing pointer reinforcement on a BST. However, we're going to use cards to explain it this time. So over the course of this trick, I'm going to use this blank card to represent where the root of the tree is, and I'm going to use this joker to represent where we are in our recursive calls. So the first thing we're going to do is we're going to add 5 to the tree. So while we only have a root, it's relatively simple. We just start our recursive call at the root, and then add our new node and return it to point to the root. Next, let's say we're adding 3 to the tree. So we start at the root, and now we're going to dereference our root and go start at our 5, and that's going to return what our root should point to. Then, since 3 is less than 5, we're going to recurse to the left of 5, and we'll find a null spot. This is where we have to return 3, which will get set to 5's left pointer, and then now we go back up to the root and reset 5 to the root. Next, if we're adding 4, again, we're going to start by dereferencing our root. Then, since 4 is less than 5, we're going to dereference our left pointer. And then, since 4 is greater than 3, we'll move to the right. We find a null spot, so we return 4, which gets set to the right pointer of 3. We go back up. 3 will get set to the left pointer of 5. We go back up, and 5 will get reset to our root. Next, we'll add 9. So again, we start every process by dereferencing our root. 9 is greater than 5, so we move to the right, find a null spot, and return that, which will get set to 5's right pointer. Recurse back up, and reset 5 to our root. Now we'll add a queen. Again, we dereference our root, recurse to the right, which dereferences this pointer, recurses over here, we find a null, so we add it. Set that to the right pointer of 9, set 9 to the right pointer of 5, and now we set 5 back to our root. Now let's see what happens when we try to add a duplicate. So we're going to repeat the process exactly the same as we have in the past. We start by dereferencing our root. We move down, since the queen is greater than 5, we detach this pointer and move down to the 9. Detach this pointer, move down to the queen, and now we find something that's neither greater than or less than the data we're currently at. In this case, we're just going to not perform any actions, not recurse either direction, not return a new node. We're just going to return where we currently are. This will set our queen back to the right pointer of 9, and then all of our normal operations will perform, setting 9 to the right pointer of 5, and resetting 5 to our root. And this queen will just go away. And then finally, we're going to perform our add operation with 7. So again, we dereference our root, move to the right, move to the left, return this new node, and all of these pointers fall into place. Now we're going to do a couple examples of remove. So the first thing we're going to remove is we're going to remove that 7 we just added. So if you remember from the pseudocode, anytime we want to perform a remove operation, we need to make sure we have a dummy node first. So I'm going to use this blank card to represent our dummy node. This will store the data that we find in the tree so that we can return it back later. So since we're looking for 7, we're still going to perform the same pointer reinforcement tricks we did when we're adding. So we're going to start our process by detaching the root. We recurse to the right, which detaches this whole subtree, and then we recurse to the left, which detaches this. Now we found the data we're looking for, so what we're going to do is we're going to set our dummy node to have the same data as the one we found. So now that it has the same data, we look at what kind of children our node has. Since 7 has no children, all we have to do is return null. Null will get set to the left pointer of 9, and then 9 will return, get set to the right pointer of 5, and 5 will return and get set back to the root of the tree. This 7 no longer has anything pointing to it, so it gets garbage collected, and we can return this data in our dummy node back to the user. The next thing we're going to remove is we're going to remove this 3. So again, we start the process by setting our dummy node, and now we traverse through our tree. Our first step is detaching the root. We look to the left because 3 is less than 5, and now we finally arrive at our data. Again, the first step in the process is the same. We found our data, so we have to set it into our dummy node, and now we look at what children 3 has. In this case, we can see that the 3 of clubs only has one child. It has a right child, which is the 4 of hearts. So we're going to return that, which will get set to the left pointer of 5, and then we return, as we recurse back up, we set 5 back to the root of our tree. Just like before, nothing's pointing to this 3, so it will get garbage collected, and the 3 that was in our dummy node can get returned to the user. Now we're going to do a more complex remove case where we remove our root, which is the 5 of spades. So again, we start the process by creating our dummy node, dereferencing our root, and traversing through the tree. Here, immediately we find our data, so we set it into our dummy node, and we look at our children. In this case, 5 has 2 children, so we're going to need to use a predecessor method to remove it. When using our predecessor, again, just like in the pseudocode, we're going to need another dummy because we need to find where our predecessor is and store that data to replace the data that's in the root. So we create our second dummy. This dummy is going to store the data in our predecessor, and we start recursing to the left. So once we recurse to the left, now we're going to look until we find a node that has a right child of null. And if it has a right child, we recurse to it. If it doesn't have a right child, we found our predecessor. In this case, we found that immediately with the 4 of hearts, so we can store that predecessor in our second dummy node. And then now we need to remove this 4 of hearts. This is going to be a similar remove operation to what we do in our regular remove method, except that it's impossible for this to be a 2-child case, because if it had a right child, then that right child would have been our predecessor instead. So in this case, we just return whatever is to the left of 4, which happens to be nothing. So nothing will get, or null will get set to the left pointer of 5, and this 4 will get garbage collected. Now we're back after our predecessor method has finished returning. So what we need to do now is we need to replace this data in the node with the data in our predecessor. So fortunately, we've stored it in a dummy node, so it's a relatively simple operation to replace it with the 4 of hearts. You'll notice that this still maintains the order property of our BST. That's why we have to use the predecessor or the successor when we remove, and not just some arbitrary data. Now that we've replaced this data, we're done with this second dummy node, and we can continue on with returning everything back to the root, where the root will get reset, and we can return the 5 of spades back to our user. I hope this was helpful.
Hope these examples really reinforce the point.
So, now we're going to talk about the efficiencies for a BST tree. In a BST tree, the average case, which represents when the tree is balanced, which means there's approximately an equal number of nodes on the left side of the tree and the right side of the tree. In that case, it's going to be O of log n in all cases. And the reason why it's O of log n, when you look at the balance case, every time we recurse through a tree, whether we're adding or removing, we're either going left or to right. And in this case, we effectively eliminate half of the tree. So if we go to the right, we eliminated this portion. If we go to the right again, we're eliminating the left portion until we find what we want. And when the log n represents the number of levels you have to traverse down in the tree. Now, let's talk about the worst case scenario. So the worst case scenario is when we have a degenerate tree. And like we mentioned before, a degenerate tree is when the tree has each node in a tree has one child, basically a linked list. And recalling the efficiencies of a linked list, the worst case for adding, removing, and accessing is O of n. And basically what this means is we'll have to traverse through every node until we find what we want, which is very bad.
And that's all, guys. See you next time in CS 1332 recitation.